that would be it. Okay, here we go. And I will share this. Okay, cool. You should be able to see my excellent and wonderful free drawing software. Okay, here we go. Oh, whoops, I need to change the setting real fast. Press this, and then, sorry, here we go. Okay, cool, we're good. Okay, so we talked a bit about stuff from chapter 2 last class, or class, what am I saying, workshop. And well, we're gonna be focusing on that stuff again, especially because the quiz is about it this week, and the worksheet is also about it. But kind of like I said, it's really core, and this is definitely the sort of thing that's just worth spending all of this extra time on. Okay, so here we go. Yet again, so this is on chapter 6 from the book. And like I mentioned, this is on the quiz, this stuff. So good to keep in mind. Okay. And the main idea is that there are these two reactions, right? And we kind of talked about what they're focused on last week, but well, I mean, just to go back through that again and refresh your memory and always keep this sort of stuff in mind, right? With SN2, you have like some carbon and then a leaving group, which I'll call LG, right? And then you have some other stuff, right? That looks like A, B, and well, I already used C, so why don't you use D, right? And then what happens is you have this nucleophile, which has 2 electrons like this, right? These 2 electrons go around here. Okay, this is what we call the backside attack, right? Okay, there was this spot in the middle. I'm moving through this a bit fast, but this is like hopefully some kind of review stuff. Okay, and then we have this like kind of intermediate state, right, where it flattens, right? Earlier it's open like this, and then it flattens, and okay, well I can't go back this far with my hand, but you know it's like this, it flattens, and then it goes that way. Okay, that's the best I could do with my hand. I'm not good enough to do anything else. Okay, here we go. Right, so it flattens, right? Some people call this like an umbrella, right? You have an umbrella that's like hanging over you. If I had an umbrella that I didn't mind breaking, I would show you. You have an umbrella, it goes flat in the wind, and then it like flips inside out, right? That's a kind of like standard analogy. Okay, and then, well, at the end we wind up getting this. Okay, and the point is that the stereochemistry inverts. Which is why we talk about the mechanism at all in the first place. Okay. I mean, I guess in general, organic chemists care about how mechanisms work, but well, as students, we care about what we get at the end, right? And this is what happens. So the stereochemistry inverts. Okay. And then SN1, well, let's say you have some tertiary carbon or something, right? I think last time I'll be consistent with how I did it before. So last time I did it like this, and then you can have, I don't know, bromine, right? Whatever. And you put it in water, and every once in a while this bromine just comes off, right? And you'll notice that at this point I'm using arrows, and this is like a thing to get used to, right? So these arrows are when electrons move. You're moving a pair of electrons. Okay, so all the electrons in this bond here, they move up to the bromine, right? Same thing over here. So this, oh man, that's so ugly. It's okay. There we go, right? So the electrons are moving over there. And then, well, here you could draw it like that too, right? I should have put that arrow in there as well. Okay. And so once we're here, well, now we get a carbocation, right? And we also get this bromine minus. Okay. So we needed that water there in the first place because we needed to make this bromine ion. And if we didn't have this kind of like nice solvent that could sustain ions, then, well, we wouldn't have a bromine showing up in the first place, right? It would be really hard to get this bromine off. We'll talk about that in a moment, though. Okay, and then now we take this water, right? And it's got a bunch of electrons on it, okay? And it's going to hop over there. Okay. And here we go. Now we have this water. It has a plus charge. Remember, this whole thing had a plus charge, and we added something that's neutral. So the end has to have a plus charge as well, right? And, well, we have this bromine minus, okay? And now if we want to be extra nice about how we do this reaction, then we could pluck off this bromine. And let me keep using my color convention. Here we go.
Wait, can I interject right here? I have a question
Yes.
about this part. So in Professor Molander's lectures, like it showed that he was using like the leaving group to kind of like rip off the hydrogen off of the water ion thing, but like in the textbook, the solvent rips off the hydrogen.
Yeah, it kind of could be either way. So I guess to like here, let me finish this one off. So once you're at this stage, right? This HBr is like an acid, or really, it doesn't have to be bromine. It could be whatever leaving group you want. And so what happens is, well, there's a bunch of water here, right? And these two are gonna.
Oh, okay.
Yeah, they're gonna do this, right? So it doesn't make a difference really. Like this is gonna happen at the end no matter what, and so whichever one you draw it as, whether you draw the bromine taking off the water, the hydrogen, or the water taking it off, either way you're gonna get either scenario 1 or scenario 2. And
would it be the same case if the solvent was alcohol?
Yeah.
Okay.
Yeah. Yeah, I used water in particular here. But you're absolutely right. So you could use alcohols to do this too. And in fact, that's a nice way of making ethers. It's one of the ways that you'll learn how to make ethers.
Oh, okay.
Yeah.
Got it. Thank you.
Yeah. Okay, so here we go. So this is what this looks like. And then, well, every single one of these steps that I drew, I could very well do the reverse, right? There's no reason that this HBr, I mean, this thing is an alcohol, right? And like we just mentioned, an alcohol can take off, or you can protonate an alcohol, right? With this HBr that's just floating around. So, okay, no reason I can't go back that way, right? This OH, just like this bromine could pop off, so could the OH, right? There's no reason it can't. In fact, H2O is a good leaving group, right? Because it's just water. So no reason I can't go back this way. And well, once we're here, there's a bunch of bromine floating around, right? So, okay, I could very well go back. All right. And the idea, once we're here, is that, well, SN1 is reversible, right? I didn't draw a molecule that was chiral, but well, because see, there's 3 methyl groups here, so this molecule can't be chiral. But if it was chiral, you lose chirality. Okay. And this is important because, well, it happens because you go through a carbocation. Okay. So whenever you go through a carbocation, you're going to lose chirality, at least at that carbon.
Does that mean that the products are achiral, or that they have or that they're like racemic?
Yeah, so it'll mean that they're it depends on if the carbon that was there earlier that you're messing around with already was a chiral center, then the end it'll be racemic, right? So if I drew this molecule instead like this, right? So that it has 4 different things on it. Well, let me use bromine again. So this has 4 different, right? So let's say this is optically pure, meaning that there's just one, right? And then let's say it looks like this. Okay, and we put it in water. Oh, wrong way. Okay, at the end, this is going to be racemic. Oops. Oh man. There we go. Okay. Because at that carbon, we have to go through a chiral intermediate. Okay. From there, it's also worth saying, like, if we have a, so I won't draw it too much in depth, but if we have a molecule with a chiral center, right, and then it's connected to another chiral center with a leaving group, right? Well, okay. This chiral center is going to stay as is because you didn't do anything with it, right? Leaving group totally unchanged. Well, there is no leaving group at this one, right? So it's totally fine. And then over here, this is going to be this one's going to be both R and S. And I did not say that it's racemic because racemic means you have the 2 mirror images, right? But instead you wind up having this chiral center always staying the same, and this one over here changes. So really you get 2 diastereomers. Not 2 enantiomers, because enantiomers are mirror images of the whole molecule at once. Okay.
And this would be optically active, right?
Yes, it would, because you still have one place that is always optically active, right? Unchanged, still chiral. Yeah. Okay. I didn't draw this one out because, I mean, working with chirality and stereocenters is already complicated enough, and I didn't want to throw an example with like 10 carbons at you. So, yeah, just.
Why is SN1 reversible?
So, in general, I guess that's a little bit of a hard question to ask or answer. It kind of comes down to the fact that this carbocation is stable. So you're able to, whatever you put on the carbocation, you're going to be able to pull off. Like, this example is as good as any for showing this because, like, we have a tertiary carbocation. For example, you could use an allylic carbocation or a benzylic carbocation. Those are kind of the only places that SN1 is really going to work. So we have this tertiary carbocation, and it's all right. It's like, I mean, it's not good by any measure, right? You make very little of it, but you make enough that you can go through this whole pathway, right? And if we're starting with just this, then, well, it's gonna go into equilibrium, or it's gonna go over to here, until the amount of OH that pops off is going to be the same as the amount of bromine that's popping off. So we have like the same amount going in one direction as the other, and then we reach equilibrium. The main idea is that regardless of which way we, or what we're starting with here, this carbocation is decent enough. So we can go back to it. That's not to say that these two products, or just that this, for example, this starting molecule with the bromine and the ending molecule, that's the alcohol, that's not to say that they're going to be made in equal concentrations, right? You're not going to have a 50-50 mixture of them. In fact, there are ways to, normally if you're doing like a real synthesis and you don't want to lose like half your product in an E1 or an SN1. There are ways to kind of drive it forwards, right? That being like really put a lot of, you could put like, well, you could heat it depending on which one's like more favorable or not. You could remove the product that you want at the end. There's a few of these different ways that you could do stuff like this. Okay. Let me get rid of these extra markings. Oh, I don't know what. Oh, oops! I erased diastereomers. Okay. So important points are it's reversible. You lose the chirality. There was a third point. Oh, and this is where we get to actually talk about the two and compare them. This SN1, it didn't really. So look, it depended on the leaving group of this molecule, right? Because we had to pull the bromine off. Nowhere in this first step did I say, oh, we need water to be a really good nucleophile, right? It didn't depend on water at the first step, right? And forming this carbocation is the part that's hard. So one of the important things here is that it doesn't really depend on the nucleophile strength. Okay. And that's a kind of good thing. Because, well, if you have a really strong nucleophile, it can do some other like messy stuff with the rest of the molecule, right? Let's say you have a molecule with a bromine somewhere else on a primary carbon, right? I mean, you don't want to mess with those things. So you can put it in a really like mild weak nucleophile, and it's gonna SN1 is gonna be like favored. It's gonna go nicely because it doesn't really matter how strong the nucleophile is that much. Okay, there are some nucleophiles that just suck, are like never gonna work. Fluoride, for example, is one of them. Fluoride is like a garbage nucleophile. It's not very good. Okay.
So, okay, just interrupt with a follow-up question. So, would SN1 be more like sensitive to leaving group strength?
Yeah, it matters how good your leaving group is. I don't know if it's necessarily more sensitive because that it'll affect the position of the equilibrium, like whether you have more of your starting material or more of your product once it reaches equilibrium. But there will be some amount of how much it comes off. Yeah, I guess there's this difference between how fast it takes it to happen and what you get at the end. There are some reactions that are super favorable, but really slow. Yeah, I think with both SN2 and SN1, you kind of want good leaving groups either way. It's generally favorable, right? You want as much product as possible, so you want the reaction to go as smoothly as it can. And that that really relies on a good leaving group. Okay. Yeah. Okay, and then, well, last week I also said, okay, well, there's this kind of table, right? So we could say nucleophiles and describe a table. There's not a ton of different types of nucleophiles that you'll see. They're generally pretty specific. There's some kind of like ways to kind of rank how good of a nucleophile there is, but it's not like the most reliable thing. It's kind of weird. I mean, you could say like the charge matters, the electronegativity matters. I think the size or polarizability matters. So size also referring to steric effects, meaning that, like, for example, methanol is a better nucleophile than, for example, tert-butanol, which is what that looks like, right? Because all of this extra stuff is kind of annoying. It's going to get in the way, right? Yeah, there's actually, I guess this is worth mentioning now because I'm just going for it. Let me go back up here, right? So this is like an example that's used pretty often. So if you have, for example, like triethylamine, which looks like this. This is a worse nucleophile than, for example, this. So let me try to draw this better. Okay, so if you see what's happening here, you are like tying back the three ethyl groups.
So usually any kind of branched structure would be more sterically hindered than a ring, right?
Yeah. I mean, for example, like, like NH3 is better than something along these lines, right? But you know that. Yeah, right. Just nobody's gonna ask you to compare, for example, like NH2 with a methyl on it, and, for example, like what I just drew, right? Nobody's gonna ask you to compare these two because how do you actually? Okay, so this one would be better. We kind of know that, right? Because this is essentially like a methyl, except there's just bigger stuff elsewhere too. But in general, they try to keep examples as just one effect at a time.
Okay, thank you.
Yeah. Yeah, anyway, so we wrote this table that was like, okay, here's some great ones, right? Iodine is really good, and then these things with sulfur, right? These sulfur anions, those are really good too. They're pretty big and polarizable and electronegative. Yet they can also be pretty small, just kind of like the rest of the molecule can be pretty small. It's just like a primary thing that's jutting out. Here we go. Here's some good ones. Bromine is a pretty good nucleophile. Oxides, so something with an oxygen minus, that could also be HO minus, are pretty good. Azide is this weird thing. It's very small. It's generally considered to be really small. And it's a pretty nasty anion, so it'll work pretty well. Here's another one, for example.
What's the subscript with the, what did you call that? Yeah, that one.
Sorry, it's a 3.
Okay. Thank you.
Yeah, yeah. So this is called azide. Yeah. Thanks for asking. If anything's ever unclear in my writing, please do let me know. So these are pretty good, and then here's some stuff that's like okay, right? So NH3 is okay. I these are like kind of common tables, and there's a lot of places that you can look them up, and everybody has their sort of different ranking schemes. NH3 is a pretty good nucleophile actually, but whatever, right? Usually it'll be specific to the reaction. So why don't I write H2O instead of OH2 like a normal person would? Here we go. So H2O is pretty good. And then, or just generally alcohols are pretty good. They're okay, I should say. Okay. And then, well, and then okay, we also can have, let me zoom out because some people might be writing them. I don't want to take that away from you. Okay, and then we also have leaving groups. Right, and similar sort of deal. We can write a table, right? There's some really great leaving groups. So some really good ones, and let me know, has Professor Molander in the recorded lectures or Dr. Callender mentioned OTS, O-tosyl?
Yeah.
Okay, good. Yeah, it's this big structure. This is really like OS, this thing, this, and then there's some extra nonsense here. I think there's like a methyl or something. It's something like this, right? Don't quote me on this structure because I don't exactly remember the whole thing. The idea is that it has a sulfate ion, which is like really nice and stable. This is the main one that we use. We don't really talk about the other ones that much, but you might see them show up. So there's also O-mesylate and O-triflate. Those are good too. Yeah, for all intents and purposes, they're going to work exactly the same as OTS and OMS, or yeah, they're going to work the same as O-tosylate for like the whole course, but yeah, it's good to have that in mind. Okay, great. So there's some good ones. Here we go. Let me actually zoom into what I'm doing here. Okay, so there's some good ones here too. So iodine's actually a really good one. I'm gonna move that one up. Again, these tables are kind of like, sorry if you put it in good already and you wrote it and you're like, oh my god, why does he keep changing it? Whatever, keep it in good. It's iodine is a good, really good leaving group, right? It's really big and it comes off. It's really happy to be an anion. It's fine with it. So that is good. It works. So good is leaving groups. So water. I should write these as ions. So if you're pulling off an entire water, then it's a pretty good leaving group, right? If you're pulling off an OH minus, that's not a good leaving group. In fact, that's a pretty bad leaving group. So bad leaving groups, we would write like OH minus. Here we go. Yeah. So OH minus would be like an example of a pretty bad one. There are a few cases where you will pull off OH minuses, but you'll see those later when you're a lot more comfortable with all of this stuff. They'll come, but it happens later. Okay, and then let's see. I don't know. Bromine is also a pretty good one. I don't know. Chlorine kind of fits in the middle here. It's all right. you could put it down here if you want. It's not great, but you could write it in there. You could write a okay category if you want, but yeah, this is roughly it. There aren't too many leaving groups that you tend to work with. In fact, the most common one is usually bromine. The reason being is because whenever you're given just a plain hydrocarbon, there's only one thing you can do to it, which is free radical halogenate, right? You usually use bromine to do that. So usually bromine is your leaving group, right? It's just the most common thing that you do. Okay. And then let me zoom out to see all this. Okay. So that's good. And then, okay, there's a few extra notes, right? They're not like crazy important, right? So we can also talk about solvent. Okay. So with SN2, you don't want anions in your solution because those anions are just going to attack whatever leaving group you have, right? Or the carbon that has the the carbon that has the leaving group, right? So that's how I usually try to remember it because, well, if you want to remember that SN2 uses polar aprotic solvents, go for it. That's something that you can just memorize, right? There's only 2 categories, so you can just remember. But you want it to be polar because these reactions are polar, right? Like you have to kick something off, right? And if you want to do that, you have to move charges around. So, okay, you need to be able to do that, right? But you don't want, so for SN2, so you don't want solvent anions. Because they will interfere. Okay, that's just bad. That's the easy way to remember it. There's some other stuff about like solvation and junk like that, but this is the kind of easy way to remember it. So okay, what are some good polar aprotic solvents? Anyone have any favorites?
I just have a question like about this.
Oh.
Polar aprotic solvents. So like in SN2 reactions, the solvent doesn't do anything.
No, it does not get involved.
So when does a solvent ever get involved?
So in SN1, it matters because first with SN1, you could attach the solvent. In fact, that's what we did it before, right? Where we attached water. So you do the whole reaction in water and you just fill it, do it there. I think there are some cases of SN1 where you do the reaction in the solvent and you have something that something different than the solvent that you're trying to attach. Really that the solvent matters there because you have to hydrate whatever you're doing, right? If you have an anion, it doesn't just float around. There's a bunch of water that surrounds it or whatever else you have. So you need something to hydrate that thing. That's how it gets involved. You don't draw that in the mechanism because nobody wants to draw like, Br minus and then like H2O, right? And then like, yeah, like nobody's gonna draw that. I think I was looking at the textbook earlier and normally the textbook is kind of bad, but yeah, it kind of gets into the stuff about like how if you want to do one of these, like an SN1 reaction, you have to solvate, and you need like a good solvent because to do the reaction, you have to pull off those waters so you can get it onto the thing, and then this whole messy stuff. I guess to answer your question though, for the most part, it doesn't get involved, except in SN1 when it can be the reactant itself.
Okay.
Wait, Hey Adam, could you go through like a solvolysis example? Because I've seen a lot of them, especially involved with like SN1 reactions. So I just want to like get some more examples of it.
Okay. Yeah, I guess could you clarify with solvolysis what you mean?
So like, say for instance, we were gonna go through like a SN1 reaction, and we put in water, like we put in like simple water, but then we have well no, water's the nucleophile in this situation, but then we put it in like some other like some kind of like solution, I guess. And they say that there's like hydroniums floating around, and the thing that actually like attacks the electrophile is actually the solution. It's not like the nucleophile kind of.
Okay. I know and this is a little bit of what I was referring to. So with well, I'll just say for here, right? So you for SN1 you want to uh solvate well, like everything, right? Ions, right? Like the intermediates, right? So you need polar protic, right? Yeah, I know that there were some examples where like uh they had, for example, like I'm just gonna keep using this one because this is like the nice easy example. Um, sorry, that's my roommate's alarm. Let me turn that off. Sorry about that. As you could tell, it's a very loud alarm. There are some examples where you could have like water in ethanol, and then okay, it would do this. And I saw this earlier, and I'm not really sure why you would do this, because the ethanol could just react itself too, and it would make side products. Um, in general, you would just put it in the solvent itself. But what does happen is in this reaction, you get like, you know, actually, why don't I even just scroll up to what we had earlier? Or get rid of all this, and I'll just scroll up. What happens is way up here, right? So you do get these like hydronium ions, and those could get involved. Like you could take these and you could use them to protonate this stuff here too, this alcohol. Yeah, I guess when we're doing this, all these things in between are really solvated. So like here, there's like this OA, this water, right? We have all these guys here in the middle. Yeah, although I mean we certainly don't draw those in because that's like kind of that would be a lot of work, and it's not, they don't tell us that much, right? Really, these should be like dashed lines. Yeah. Yeah, I think with SN1, so just speaking from like experience with doing all these problems, for SN1, it's really generally going to be you put it in the solvent and it does the reaction. Maybe I should add, I think there are some examples where they'll have like you could do stuff like this, right? And then you could have like chlorine in water, and maybe this is what you were getting at actually. And so, right, you have something like this, Cl minus. In fact, why don't I even make this a kind of better example, right? So if we have this as an alcohol, here we go. This is a good example now. OH, right? And we'll say, okay, this water here, I'm going to use my coloring scheme, right? So for example, this water will go and pull off a hydrogen, right? And we just said this is a decent leaving group, right? I actually probably even called it a good leaving group, right? And now here we go. I mean, we could, you know, pull this thing off, right? This carbocation is like good enough, right? It's serviceable. Here we go. And now we have a chlorine ion and we have just more water, right? And okay, now we can, you know, we can go in. Yeah. So you could do this with SN1. The kind of important idea is that this is dilute. Okay. You will see shortly why it needs to be dilute, as in next week when you talk about E1, or actually you've already talked about E1, haven't you? Or at least you're expected to know it apparently, right? So this is a good moment to say E1. Just to finish what I was writing up here though, with SN2, just going back to finish up the solvent stuff. So you could use acetone as a solvent here, right? The reason I say we should finish this is because you just have to remember like one SN2 solvent, right? And you'll just use it every time, right? Nobody's ever gonna penalize you for saying acetone every single time. And it just makes your life a little bit easier. But well, it's good to know a few, right? So acetone is a good one. So I know DMSO, which is dimethyl sulfoxide, if you like, is another one. DMF is dimethyl formamide or formamide, which is like this thing. So someone wrote DMS. Can you remind me of what DMS is, or is it supposed to be DMSO?
Yeah, I meant to write DMS up.
Okay, yeah. That's a good one. Here we go. So acetonitrile, you might see. That's one. Okay, I think that covers it, right? Yeah. So these have no OH or NH. That's what makes things polar protic, is if they have an OH or an NH. Okay, and then, well, polar protic, now that one's kind of easy, right? We have alcohols, and you can have things with NH, right? Those are the two things you could use. Okay. And there's also sorts of variations on those things, but you don't need, I mean, if it has an OH or an NH, it's polar protic. Okay. Zoom out. This is the big picture, right? SN2, polar aprotic. SN1, polar protic. I don't have any good mnemonics for remembering it besides like whether you want ions or you don't want ions. If anybody has any good mnemonics, let us know and I will use them for eternity. But this is the way that I just think about it. Okay. Nice. Okay, and then, well, E1, which we should mention, So E1 usually happens in one context, okay? So so there's mainly one context for E1, okay? And that is when you take some alcohol, right? And then you give it concentrated acid, and you usually use sulfuric acid, and then you heat the shit out of it, okay? And what happens is you make a double bond. All right. The way this actually happens is, well, you protonate there, right? So this becomes a plus here. This comes off. Okay. Well, look, there's all these hydrogens, right? So what happens is you take the conjugate base of whatever you used, right? So in this case, it'll be like this thing. And then it'll just pull one of these hydrogens off. Okay. And those electrons are going to go here and they're going to make this double bond. A theme with the one reactions, right? E1 and SN1, this is also reversible, right? In fact, if you want, this is your first reaction that you've learned that uses alkenes or double bonds, right? So there may very well be a question that asks like, okay, let's say I have this and I put it in dilute H2SO4, okay? This time we're using dilute because we want to go the opposite direction. Up here, we're using concentrated because we want to force it to go in this double bond direction, right? Because once this water comes off, it's going to be really happy in the sulfuric acid. Another way to say it is sulfuric acid really hates not having water. It doesn't want to be concentrated. So if you're giving it water, it's going to do everything it can to hang on to that water. So it's not going to want to go in the reverse direction. Okay. So this really pushes it in to favor this, the double bond. But over here, we could do dilute sulfuric acid, right? Put it in a whole bunch of water. Just give it enough acid to put a proton on that double bond. And then, well, the water, the alcohol is going to stick on there. Okay. And here's the thing. I said the water sticks onto this carbon, right? Why didn't I say that it sticks onto this carbon, the one at the end? Well, now we look at the mechanism.
Secondary better than primary?
Yeah, exactly. Right. So look, now we can look at the mechanism, right? So here's the thing, right? We're going to take these electrons, and we're going to pull off that was a truly atrocious arrow. Oh man. Okay, we're going to pull off one of these hydrogens. All right. And so we could do it in two ways. So one of them we could put the hydrogen on. How would I actually do it? One of them we could put the hydrogen on here, and we'll get a plus charge on the end, on the primary carbon. Okay. The other way we could do it here, and we could get the plus charge on the secondary carbon. What do we know about carbocations? What is like the thing we know about them?
Substituted is more stable.
Yeah, they don't like being on primary carbons, right? That's not for them. So okay, well, this one is less stable, right? And so we take this, and now we're off to the races, right? And we can go up to here. Again, reversible, but like we add so much water that it's gonna be forced in this direction. that's so this is a reaction that well, if you're talking about E1, this is a reaction that you've learned. So we get, more bang for our buck, so to say, right? We get two reactions for one mechanism.
So when drawing the arrows, like, should we do the like different sized forward and back arrows depending on if the acid is dilute or concentrated?
No. You could
They
just
don't
write
care.
no. You could just write normal reversible. In fact, so for these, certainly for E1, so for E1 up here, you're adding so much concentrated acid, and you can get sulfuric acid really damn concentrated. It's gonna go more or less to completion, as close as you can get it. Similar thing here. You add so much water that this is like this can reasonably happen. Yeah. There we go. It's a 2-for-1 deal. If you want. Yeah.
So Adam, so with the dilute sulfuric acid, is that like a SN1 reaction or can you just like quickly explain like concentrated sulfuric acid versus like dilute sulfuric acid again?
Yeah, so the mechanism is still the same in both cases. I literally drew the same thing just backwards. Well, slightly different because I moved the double bond. But the reason we use concentrated in this case is to force the reaction in the forward direction. Right. The actual reason for why it forces it in the forward direction is because, well, it gets a little complicated. The idea is just that there's not a lot of water, so there's not much room to go in the reverse direction. But when you get more into it, it's also that sulfuric acid, like, it is super, like, thermodynamically favorable, if you want, for sulfuric acid to grab onto water. Right? So once sulfuric acid grabs onto the water, it's not going to get rid of it. That is, when it's hydrated, or when it's concentrated, at least, that's what happens. Right? Down here, that.
So wait, let me just like kind of confirm. So the one in the bottom, like the dilute reaction, is the reverse of what we did in the top.
Yes.
Okay.
Same mechanism.
Yeah.
Just drew it backwards.
Mm-hmm.
Yeah. Yeah. The minor distinction being that I moved where the double bond is, just to show you that it goes on the more substituted place.
Got it. Thank you.
Yeah. Okay. Yeah.
So dilute sulfuric acid would just like force it in the reverse direction.
Yeah. Another way to think about it is you have so much water in this case, right? Because you're just putting enough sulfuric acid in to like get this going. You have so much water in this case that you're gonna just put all that water on because there's no shortage of water, right? There's like 1,000,000 times more water than there is this molecule. So just load a whole bunch of it onto it. Yeah. That's a way to think about it. Yeah. So okay. So this is how E1 works. Yeah, this is I think in theory there are like some other things you could do with E1. In like 2 or 3 years of looking at Chem241 exams and doing all these practice problems, I don't think I've seen examples where it's not just putting a bunch of concentrated acid on, right? So when you see E1, this is what you should think of. You should think of, you have an alcohol, you add a bunch of sulfuric acid, and you get a double bond out at the end, right? You don't, this is not one of those reactions where you go into generalities and you say, oh, I have a leaving group and then I do this, and then at the end I get some sort of product. No, you have an alcohol, you add really concentrated sulfuric acid, and then you heat it to death, and you get a double bond at the end. Okay? That is usually the way to think about it. Right? So this thing that I drew at the end here, this is E1 in reverse, which we might call hydration. Okay. Yeah, although you will see this reaction again. This is actually E1, like this here, right? This thing. What I drew after is like, you wouldn't call that elimination because you're not pulling something off, right? You'd call it addition, but this is it. This is E1. Like when they ask you like draw an E1 reaction, this is what you draw. Okay. Here we go. Someone's asking, can we talk about shifts in SN1 and E1 and specifically when we expect them to happen? Yeah. Oh, look at this. Oh man, I ran out of space on the page. Okay. Yeah. How about new page? Okay. It's a long page, as you could tell. So we really talked about a whole bunch. Let's see. Oh, is it not? Oh man. Okay. Hang on. Let me close this one and then. Okay. All right. Cool. Now it's working. Here we go. SN1 and E1 and when we would expect them to happen. Yeah. So I actually had a note about this that I thought was good to talk about. So with SN1 and E1. I hope you guys don't mind that we're taking so long in the review today, but I figure it's probably useful, right? I think you guys can get behind it. If somebody is like, screw that, I want to do the damn worksheet, I'm really sorry, but we'll keep going through the review because this is like the stuff that you'll see. So rearrangements happen when you're doing SN1 or or E1. They do not happen in SN2. Okay, sorry, I know they startled some of you. They don't. SN2 happens all in one step, right? You maintain chirality. Like literally everything is perfectly lined up and coordinated, and nothing. There's no time or space for anything to move around, right? Here, SN1 and E1. We can get rearrangements. We can get things moving around, okay? So there are two things that can happen, right? So one of them is called a hydride shift. These are both called shifts. So the first one is a hydride shift, meaning we move a hydrogen, okay? So like a good example of this would be when, for example, we have this bromine. So let's say we have something like this, right? And then, okay, well, we put it in water, right? And why don't I'll draw it going down because I'll show you what the final product is at the end here, right? So we put it in water, and what's going to happen? This is one of those situations where you really have to draw the mechanism out. It's important, and this is something when you're doing an E1 or SN1 that you really like every step of the way. You think like, okay, do I have a carbocation, and can it do a rearrangement? So here we go. Okay, we're going to pluck off this bromine, right? Well, it's just going to come off itself. And there we go. We have this Carbocation. Oh, whoops. I drew this molecule. Okay. Let me readjust. Sorry. I've learned that apparently in teaching, like, it's really bad practice to write something and then like erase it and then have everybody like go back in their notes and be like, shit, I wrote that wrong. So I'm sorry. But if we have this and then we pull off that bromine, right, we'll get this carbocation. And this is a secondary carbocation, right? That's not really that good. No. We know that this, well, so I should have said, right? This is SN1 because water H2O is not really a good nucleophile, okay? Okay. Jumping around a bit here, but I should have justified why it was SN1 in the first place, right? So here we go. So it's SN1 because this is not a great nucleophile, okay? It's not going to have like the nucleophilicity. It's not going to have the charge or the favorable things that allow it to just backside attack and take off the bromine, right? It's a secondary carbon. Doing SN2 on a secondary carbon is already hard enough. So here we go. This is, now we have a secondary carbocation. Okay. But we could do better, right? And we know we can do better because look at this hydrogen right here. Hydrogens are really small. They're very light, right? It's like one proton, right? Do you know how small a proton is? It's really small. So this hydrogen could just move. It's hard to do, right? It's way heavier than electrons, for example, right? It's harder to move protons than electrons, but you could do it, right? It's pretty small. It's possible. And so this whole thing is just going to move, right? The whole thing is going to shift. And why don't I even use, look at this. Oh yeah. Wouldn't be able to do this in real person, right? Let me use a different color. And look, here we go. It's, the whole thing will move, right? And what that means is we go here, right? And look, we just put that hydrogen onto there, right? And now, so I should have said there is another hydrogen on there, right? Just to fill in, because for a moment while talking, I had a brief moment where I was like, oh my God, my carbon only has 3 bonds. I'm screwed, right? No, there's another hydrogen on there, remember? And it's always helpful to draw them all out, just because that way you know that you're not making 5 bonds or just 3 bonds or something, right? And then over here, I guess I was about to draw a hydrogen, but we just got rid of it, right? Put this over here. Now this is a tertiary carbocation. That's nice, right? We can really work with that. So now that we're here, well, now we could just take our water, right? And I'll leave you to fill in the rest of the steps, but there we go. Okay. The rest of this is just this water, this H2O sticking on there. Remember, these electrons from the water, they're the ones that do they're the muscle, right? They're the ones that do all the heavy lifting. And then you pull off one of those protons, right? Or sorry, one of those hydrogens that's on the water, right? Because the water is going to have, the H2O on the molecule is going to have a plus charge, so you pull one of those off. Okay. So here we go. Okay. That's what like the rearrangement does. Here's an important part. Okay. I see there's a question, but one moment. So here we go, right? This first step, we can go backwards, right? Same as a usual SN1, no problem. We could do that, right? Are we going to go backwards from a tertiary carbocation to a secondary carbocation? What would be the point, right? Why would we move the hydrogen again? It already took a lot of work to move that hydrogen, right? Yes, it's light, but it's a lot more work than just moving some electrons around. Right? Why would we have done all of that work just to go back, right? Why would we make a secondary carbocation? It's way less stable. Okay. This does not go backwards. No, it doesn't do it. Okay, this is actually a forward direction reaction. It goes one way and it doesn't go back. And well, okay, these are reversible, but we don't really care, right? Once we're on this side, no going back. Okay, we're on this side and we're here to stay. All right. So if we were to do this reaction, right? Yeah, we just drew all this out, and that's really nice, right? But well, in general, I mean, like 3 months from now, nobody's gonna say like draw out the mechanism every time. No, right? They're gonna say, okay, what's the product, right? So what do we actually get? Yes. So to answer the question in the chat, which is where I was going, yes, you get 2 products. Okay. Oops. Okay. So we get both of these.
Will you have more of the shifted one?
That is a hard question to answer. It depends on what you're moving and how much like stability you gain out of it. Usually it'll be the same between each, because you'll generally be going between from a secondary carbocation to a tertiary carbocation. So the shift in energy, the decrease in energy is probably going to be pretty low each time. But I guess it'll depend on what that actual change in energy is. Yeah. So there's also like a more nuanced note to make here, which is that there's this difference between like, well, moving that hydrogen is like really, it takes a high activation energy, right? Like there's a lot of work that has to go into it. But once you do it, you're in a really favorable state. So it depends on how hot your whole system is, right? Like if you put a lot of heat into it, you'll get more of this guy, right? If there's not a lot of heat, so you can't really do that hydrogen thing, then you wind up getting more of this guy. This is an idea that you'll see showing up in Orgo 2 more. It's not focused on as much in this class, which is there's this idea between a kinetic product and a thermodynamic product. So the kinetic product is the one that's easy to make, no hydrogen shifting, right? The thermodynamic product is the one that's more favorable, it's more stable, but you have to put more work into it. Yeah. Yeah, I believe that's right. I sure hope so. Yeah. It's a more nuanced note. There's some reactions that you could do at cold temperatures, which will give you different products than if you do them at hot temperatures, is the kind of idea. And this would kind of be one of them. Yeah. Okay. And then, well, there's whole alkyl shifts, right? So this is one thing, right? So I wrote 1 hydride shift, and then down here, so there's 2. So we could do whole alkyl shifts, right? And so we're moving whole carbon chains. Okay. And the one that I like, the example that I like, which, well, it's not just me who likes it, so it's good to know. It's good to know what this example is. if we take, and you might have already seen this example, and I'm not sure if you have, but if you take a ring like this, right? 4-membered rings suck. They're really bad. They're not. It's hard to make them. They're not. You have to squeeze the carbons together, right? If you take your modeling kit and you try to make one of these, you'll get into some trouble. It's not good, right? So if we put this thing in water, yeah, okay. I've been using water a lot. Let me do something a little bit more interesting, right? Here we go. Ethanol. There we go. Yeah, that's a cool one. Okay. Here we go. We put it in ethanol. Okay, all right. We do the usual, right? Here we go. Plus charge. This plus charge that's not good, right? A primary plus charge is like terrible. That's absolutely awful. It's bad, right? But you know what we could do, right? Yeah. Well, we're talking about rearrangements, so you already know what it is, right? So we're gonna take this whole bond, right? This bond, and we're gonna move it to be between these two. Okay. I drew this in a kind of weird way. There's a reason for that, right? It is very easy to take something that looks like, so at least for me, and well, maybe some of you also think this could be hard to keep track of. So if you have something like this and you draw like this, it's going to be hard to, like, there's a certain point where the points of what you're drawing, right? Like all of these things where the carbons are, and the lines become confusing, right? It's really easy to lose track of how many carbons you're actually working with, right? So the point here is, right, it's very easy to do something that looks like, okay, I don't know how in this situation it would happen, but let's say you have like a longer chain, right? If you have something that's like this, right, it's really easy to do something that looks like this, right? But this is wrong. We added a carbon on accident, okay? So counting carbons is good. Doing things out carefully is also really good. Places like this, once you get more into it, it's going to be really easy to lose track of these things. So I drew it in this particular way because, well, we're taking this whole bond and we're moving it. Okay. And then we got to keep track of where this carbocation lands, right? So why don't I actually do this out carefully and number everything, right? This is like the most foolproof way of not losing track. Here we go. So carbon 1 lands up here, 2, 3, 4, and 5. Okay. Now this is easy, right? This plus charge, it didn't move anywhere. It stayed on carbon 1. So here we go. It stayed there. Okay. Carbon 5, on the other hand, it started with 2 carbon-carbon bonds and it ended with 2 carbon-carbon bonds here, right? Carbon 5 is good. No charge. Nothing changed with carbon 5's charge. So this is better, right? We went from this primary plus charge to a secondary plus charge. That's better, right? That's certainly better. And well, now we add the alcohol into the mix, and that's what we get at the end.
Wait, Adam, why wouldn't the plus charge go on the 2?
You're right. Thank you. Yes. Yeah. The plus charge would go onto the 2. You're right. This carbon 2 started with 3 bonds, and now it ends with 2 carbon-carbon bonds. Okay, thank you. See how easy it is to make a mistake with these? Yeah.
Wait, why does it move from 1 to 2 then?
Yeah, so in this case, it's because this carbon 1 only has 1 carbon-carbon bond, and now it has 2 carbon-carbon bonds. If we draw in the rest of the hydrogens, then we'll be able to see what's going on. So right, so here's this plus, and then this guy has 1 hydrogen, right? And then now it becomes this with these 2 hydrogens stay, and this 1 hydrogen stays, but it has nothing else. Yeah. Thank you for pointing that out. See, for all of my saying that you got to keep track so carefully and watch out for these things, it happens. So do be very careful about that. It's easy to lose track of these things.
And on the ring, wouldn't it not really matter which one we put the plus on? Because wouldn't it just be able to resonate?
Yeah. Well, not resonate in this case because we don't have any double bonds to move things around. But I mean,
You can rotate.
just yeah, right. You just rotate the rings. It's the same thing. Yeah, it would matter. It would matter if I had something that looked like this to start. Whoops. Oh my God! Oh, I just hit the pen. Sorry. Okay. So if I had something like this, right? I put the plus charge over here. Now it matters because this thing will rearrange to look like that. Okay. Now here's a fun question. What happens now? In this second example.
Would it be a hydride shift?
Yeah. In case you thought you were done, you get a hydride shift. Yeah. Nasty, huh?
In terms of like an alkyl shift versus a hydride shift, would like an alkyl shift only be preferred if it's like relieving ring strain versus like a hydride shift because like it takes less energy?
Yeah, usually if you could do a hydride shift, it's usually going to be better, more preferred. This example that I gave is actually a little bit like weird because, well, I could do a hydride shift, right? Like I'm able to do it there. But relieving that ring strain is like also really favorable. So you'd wind up doing sometimes you would get a hydride shift, sometimes you would get a ring expansion. It's good and it doesn't hurt to draw both as products.
Okay, thank you.
Yeah. And I should add, so for alkyl shifts, I could draw something ugly like this, right? And then say, okay, I'm putting this thing in water, right? Well, all right, this thing is gonna be reversible, and we're gonna get a plus charge there, right? And look, nothing next to it has any hydrogens. So that means the only thing we can do is move this whole carbon. Right, let me get my blue. The only thing we could do is move that entire carbon. Whoops, I need to actually draw an arrow, right? And not reversible, again, just to really drive the point home. You don't need to draw something like this in your quiz, but okay. So we have now, we moved the plus charge, right? And then that means our final product is going to look like this. Okay. as an example of what we could do. So we'd only have one final product. It would be this plus, oops, not plus charge, but plus, you could also get the normal no rearrangement product. Okay. Rearrangements don't have to happen. Is it always the case that you get both then? I will need to, so I need to check, because, well, so this with no rearrangements is reversible back to the starting thing, right? And well, the one with rearrangements is forward, right? You don't go back. So it might be that like all of this stuff, yes, you can form it, right? But it'll just go right back to there, and then it'll get depleted and it'll become the rearranged product. I don't know if they expect you to say that. I will have to check. In fact, in the last like minute or two of the workshop, I'll go through like, well, I'll look through like some of the past research that I have, and I'll see what they expect you to write usually. Because I can't remember what their standard is exactly on whether they want you to show both or just one. You could be sure that in a question like this, they are looking for you to find the rearrangement, but I can't remember if they want you to show both products.
So Adam, like going off of that, so for your first example for alkyl shift, where it could either be a hydride shift or alkyl shift, for that one, would you be expected to show both rearrangements?
Yeah, I think you should show both.
Okay.
Yeah, I think the ring strain is going to be the more favorable one, but this is I should check. I should check what they're looking for usually in one of these problems. Because it could be both. Ring strain is kind of what you want to do because it'll be a 5-membered ring is just so much better than 4. But I'll look and see what they normally want. Yeah. Okay. Whew. An hour and a half of review. Not bad, guys. Yeah, that's okay. That's the actual like review talking that I had to do. I came up with just a few like practice problems that you might want to look at. There's not too many for just SN1 and SN2, right? If this was a week from now or 2 weeks from now, don't worry, I'll be coming up with practice problems like crazy. But just for now, some basic ones, and just because they're not on this week's worksheet, but you're finally getting into territory where you can do synthesis. Okay. Maybe that's exciting right now. You will come to hate them. No, you might not. They could be hard to approach. There are some strategies for it. You'll be learning them more and more. But for now, you know a few categories of reaction, right? You know free radical substitution, and you know substitution, SN1 and SN2, right? There's E1 also, but like, well, E1 you're just making a double bond. There's a little bit more to say about it than that, but I'll mention it briefly, and then we'll do our worksheet, like, you know, actually do it. Okay, so here's some practice, right? So let's say we start with this. You're given this molecule, and you want to go to here, this alcohol. Okay. All right, we're starting with this. What do we do? There's one right answer and no other right ones. So what do we do?
Free radical halogenation.
Yeah, right. So, okay, there's no double bonds. We could use BR2, but just to remind you of how useful it is, we'll use NBS anyway, right? We don't need to because there's no double bonds, but screw it, whatever, we'll use it anyway. And then we'll use light, H mu, and then okay. It's going to go onto that tertiary carbon. All right, and now how do we get to this final product?
Water.
Okay, what type of reaction is that?
Oh, is it one of the substitutions? I don't know which one. SN1, I think.
Yeah, there we go. The crowd came in clutch there. So yeah, so this is SN1. Okay, you put water, happens by SN1, and well, the nice thing about synthesis problems is nobody cares what the mechanism is. If you write the right product at the end, doesn't matter. You don't have to go through the whole all the stuff about SN1. That's it. Okay, that's the final product. There we go. You've done your first synthesis. It was 2 steps. That's not that bad. They'll ramp up. Yeah, here we go. Okay, let's see what else. So
Adam, I have a general question. So for these
yeah, of course.
synthesis questions, are you allowed to choose the nucleophile?
Yes.
Okay.
Yeah. There are going to be some cases where they tell you do the synthesis using compounds containing no more than some number of carbons. You're not ready for that. So hold off on those. When they come, you'll be wishing you were back at this point. But yeah, for now, don't worry about it. Okay, so we start with this ring. I draw circles. I should specify circles mean this. Okay, these 3 double bonds. I draw circles because I'm way too lazy for that. So here we go. There's a triple bond here. And then there's another carbon that goes out to this. Okay. All right, step 1, what do we do? There is only one right answer. So
Is it SN free radical halogenation and then SN2?
yes. So, okay. Here I'll use bromine just to really emphasize the point that bromine can't do anything with this aromatic ring. Or sorry, I should say the phenyl ring, but whatever. Okay. So we get benzylic bromination. Okay. And now, okay, we're doing SN2. So if you were to guess a good nucleophile, you would get this thing. Okay. For something like this, though, they're going to want you to tell them how they got it. Okay. So how do we get this? You weren't expecting this one to show up, but how do we make this compound?
Do you somehow make it from like acetonitrile because it looks like it has the same like triple bond thingy going on?
Replacing
but, like, can
that
you replace
nitrogen,
the nitrogen? Is that not possible?
It'll be really hard. It'll be really damn hard. Yeah.
Isn't this expanding like the carbon skeleton? So it's like you just go ahead and do the SN2 by doing the transition state and everything.
Yeah, but well, that's on this. We're doing SN2 to take this bromine off, right? But making this anion here that we want to use in the SN2, that's not SN2. That's a different reaction, which you have learned. It might not be coming to mind. So how about I say this? What if we start with this? What can we do?
Deprotonated.
So in this case, you want to deprotonate, right? You want to take off this hydrogen. Okay. What's really good at taking hydrogens off of things in general?
Bases.
Yeah, right. You want a base. Okay. So you want some really strong base. If you remember, hopefully you learned this, and I'm not just throwing this at you out of nowhere. So this hydrogen here has a pKa of like 20 to 25, I think, or something. All things considered, that's pretty acidic. Given that a normal alkane hydrogen is like a pKa of like 50 or something, right? That's never coming off. In this case, though, I mean, this is a fairly acidic hydrogen, right? So if we give it a really, really strong base, then we could do it. What's a really strong base? I'm going to use sodium amide, NaNH2. That minus charge on the nitrogen is going to really want to pull off that hydrogen and make NH3. It's gonna happen really easily. You're gonna get like all of this. These excellent acid-base reaction. Okay. So this is an acid-base reaction here.
Do you have to explain how you got the first thing, or just how you get it into like an anion?
No.
Okay, so like the acid can just be like, you have it, and then, right?
Well,
you have to explain how you get the nucleophile, but you don't have to explain how you get the acid.
Like
the precursor
so like
to that.
how you get this thing? No. They might even tell you like you can start with this compound too. Yeah, they probably would tell you something like that.
Wait, Adam, so in terms of like synthesis, I do remember him saying this in like the E2 video. When we're starting things off, it's typically like gonna be a free radical bromination. I just remember him saying that, oh yeah, we would use bromine a lot. But is that just like a general case?
Yeah. So the rule is always, if you start with something that has if you start with something that is just carbons and hydrogens single bonded to each other, you have to do a free radical reaction at the start. You must. There's nothing else you could do with it. I was very specific about it because like in like 5 months you'll learn that like you could take something that looks like this and there's actually a whole lot you could do with it because it has this aromatic thing. But that's for another day. But for now, if you have if you're given something that looks like this, right? And I could sit here and draw carbons all day, right? And it looks like this, and then there's one over here, and there's one over here, right? And go on and on. There's only one thing you could do. There's nothing that we can do besides this. Okay. I should say, yeah, you could do chlorine too, right? We don't normally do chlorine because it gets messy. Iodine probably won't really work. There's some stuff about iodine that makes it not really good at this. It's this. It's free radical brominate. Okay. It's selective, so we know what we're gonna get out at the end. It's the one thing that works, right? It's the only reaction you'll learn on just something that looks like this that'll work. Yeah. So So he said specifically free radical bromination. Yeah, I mean, he's right. Whenever you're given something that's just carbons, hydrogens, and single bonds, you have to free radical brominate. Nothing else you could do with it. Okay. Once you get double,
is
sorry?
SN2. Sorry.
What was it? How will we?
Is SN2?
Oh, this one up here.
Yeah.
This is a strong nucleophile.
Oh,
It has the minus charge, so it's gonna want to like get in there right away. Plus, like, this is another way to think about it, right? We had to use some really strong conditions to make this, right? That means it's not normally very happy, right? Like we had to put some real work into making this thing, so it's gonna be like a, you know, pretty fired up and ready to get it to attack, right? Yeah, you'll have noticed this whole product here, or rather I should say here, this is benzylic, right? This bromine is benzylic. Benzylic things go through SN2 pretty well. You could do SN2 on them nicely. If it was a regular secondary carbon, this reaction would get messy. In fact, you would likely do E2, but next week, right?
okay. Thank you.
Yeah. Yeah. The main thing being it's a pretty good nucleophile, and it's a benzylic carbon, so it's going to be so SN2 will go nicely. Yeah. Okay. And then, oh my God. Okay. How about I write the rest of these problems? You guys can work on them, or I'll email me and ask me questions about them. And then we'll run through the worksheet. But fortunately, we've talked a lot. I've talked a lot. And this actual worksheet should be like a nice review, right? So how would we do this? Right? And I would say, well, start with these two components and make your way to the end. Okay. That's one. Yeah. Okay. There we go. How do you get from this allylic bromide to this allylic alcohol? Okay. And is it optically pure? Is it optically active? Right. And then just one more. Is optically pure, chiral, active, whatever you want to say. Right. Yeah. Okay. That is all of those. Okay, let me actually pull up this worksheet. Okay. Post the answer to these. Oh, to these? Yeah. Okay. All right. Yeah, I'll put up some answers to them. I'll just fill them in on this worksheet when it's all said and done. Okay. Oh no, some folks are leaving. Yeah, we haven't even got to the worksheet. No. Yeah. Okay. How about we do the last ones on the worksheet? These are the important ones, and then the rest of them are just like good for like review and stuff like that.
Is the cat one important?
Of course it is. Yeah. Here, wait, let me save this and just make a new document. Oops, save. Oh yeah, create. Okay. There we go. Okay. Okay, here we go. Here's this problem. All right. Let's see. Predict the product for these reactions. Okay. Sodium cyanide in DMF. What does that tell us? What type of reaction?
This
SN2.
reaction.
Yeah, so it's SN2. Okay, cool. So it's SN2. It's going to be SN2 on the bromine. Okay, easy. We know we're going to get the cyanide out. This is a chiral compound. Is it optically pure?
Yes.
Yeah, okay. There we go. It's optically pure. And in fact, we can tell you exactly what the stereochemistry of this thing is because it goes back. Okay. We know that. Here we go. Here's another. NaO-methyl, and it's in methanol. Okay. So what is going on with this reaction?
I think it's an SN1 reaction because it's in that polar protic solution. In terms of like the NaO-methyl, that'll dissociate, leaving like a negative charge. But I think that the methyl group, it could possibly be a hindrance. So the bromine will detach off. It'll create a carbocation. And then once that happens, that's when the O-methyl will come in and attach to it.
Okay.
Redshift 2.
Okay, so yeah, it's possible that it could be a hydride shift. This bromine coming off is going to be pretty unlikely, like in the first place, because it's going to make a primary carbocation. What really kind of decides what reaction this is this nucleophile. Okay. O-methyl. That's a good nucleophile, right? So the methyl it gets in the way a little bit, but it's for the most part, methyl is a really small group, right? If it was like O-tert-butyl, if it was like this thing, that would really get in the way. It's kind of weird to think about this, but really you have to think about it as like, here's this oxygen, right? And then here's this big thing at the end, right? And this oxygen is pretty small compared to the rest of it. Whereas with methyl, it's like this, and then like, oh, here's a CH3, right? Which is kind of like, there's this whole thing, and then there's like this little thing. And anyway, this reaction is going to be SN1. You have a primary substituent, right? That bromine is just like, opening itself up to be taken out, to be removed. And what seals it there is that you have a good nucleophile too. O-methyl is a good nucleophile, right? It's in methanol, even though, so methanol is not a nice solvent for this, right? I mean, we talked about it. We want polar aprotic. The reason it's in methanol is because if you want to make sodium methoxide, NaOMe, what you do is you take methanol and you put a block of sodium in it, like sodium metal. Sodium metal is really reactive. There's some fun videos you could see online of it like blowing up because it like reacts with water, right? It reacts with alcohols too. That's how you make sodium methoxide. So that's why it's in methanol. If you moved it to another solvent, it would just like attack that solvent. So it has to be in methanol. But this is SN2. Okay. So we wind up getting that.
So would you say it would be more likely to be SN1 if it was like that oxide with the tert-butyl, like that nucleophile?
It's harder to say. If you had sodium So even if you did have if you had this, it would still probably be SN2. This is still a pretty good. This is still pretty strong. It's sterically hindered, and it'll get messier, right? There's a sort of like, I use this term messy all the time, and there's some times where like things do get messy, right? Like, here's a really like ugly reaction, right? And if somebody gives this to you, then like they're evil. Like if you have like a secondary thing and you put it in, I don't know, what's one of our like okay nucleophiles? I don't know. I can't think of a like a
Ammonia
okay.
or like NH3.
Yeah, this will probably get ugly, right? Like it could, there's some, you can make arguments for either SN1 or SN2. It's just gonna like, nobody, we don't want, hopefully nobody ever gives this to you and you never have to think about it. Yeah. Well, okay, way later in the course, you will think about a reaction like this, but that's just because it's NH3 and that's a particular thing. But anyway, there are other ways of doing this that don't involve as much ugliness as this reaction does. So this one does wind up being SN2. This important one. Okay. All right. Okay. This next one, this one's easy. This one's easy for us to tell, thankfully, right? What's going to happen?
SN1 solvolysis.
Yeah, so it's SN1, right? And then, okay, we're going to make the ether. Is it chiral, racemic, optically active? Anyone?
Racemic?
Yeah, so this is racemic, right? This carbon here has 4 different substituents on it, so it is a chiral center, but we lose stereochemistry in the reaction, right? We make a carbocation. We have to squish it flat, right? And for that moment where it's flat, you can either go from above or from below. So it winds up being racemic at the end. And here we go. Okay, HCl, we're adding a lot of acid. What are we going to do?
SN1.
Yeah, okay. So in this case, we're going to do SN1. Why don't I
So
call
they don't
this...
they don't like write a solvent. Is it typically end up being SN1? Because it would be like the, or that's just because they know, because HCl will be in water.
You would have water.
Okay.
HCl. I mean, you could get like pure straight HCl, but it'll probably mess up this molecule anyway. Yeah, it's oftentimes it'll be assume water if no solvent specified. Yeah, that's kind of a typical assumption you can make. Yeah. Okay. All right. So SN1, and then okay, here we go, and you could guess again it's racemic, right? And just for bonus points, if I say this is really concentrated, what do we get instead?
E1.
E1. Okay, and where's that double bond go?
Between the second and third
1, 2.
carbon?
Yeah.
I mean 2, 3.
Yeah, it's between the second and third carbon. So with E1, and I didn't mention this too much earlier, but it's just like a note to make. So you form whatever alkene is the most stable. Whoops, stability. right? So that goes like so the most substituted is this is most stable. Okay, and then the least substituted is.
Does most substituted just mean most like not hydrogens?
Yes, exactly. Yeah, so this is better. Oops. Okay, so we have these, right? And then we could have one hydrogen on there, right? Then if we have two hydrogens, well, a trans double bond is the best because we still have two carbons, but they're not bumping into each other, right? And then we'll, we could take a cis double bond that we can live with it, right? Right, and then so if it has one substituent, then it's okay. I'm gonna fill in with one extra. If the carbons are on the same side of the double bond, then they bump into each other extra much. So that's not as good, right? So we form whatever is most stable. In E1. Okay.
So does it have to specify like concentrated or dilute to be E1?
So yeah, E1 again. E1 is really like only ever going to happen when they specify concentrated acid, and even more so, I should have also said heat.
Okay.
In fact, in general, E1 is also E1 is only sulfuric acid specifically, but for this case, okay, I still used hydrochloric acid, but usually it's just sulfuric acid.
Okay, thank you.
Yeah. Okay. There's this alkene stability, which is good to know. One of the questions in this worksheet is about labeling double bonds if they're E or Z double bonds, or alternatively cis or trans double bonds. That's a review from stuff before. We'll skip that. There's a table in here that is nice and it is helpful to do, and it really could help keep track and review all of this stuff. So I would recommend looking at that table and going through it. Yeah, it talks about the rate, the differences between SN1 and SN2 being the rate law, the thing that actually like slows the reaction down, so carbocation stability or steric hindrance. It talks about like what type of carbon is good, so primary, secondary, tertiary, benzylic, allylic. Whether you want strong or weak nucleophiles. So remember, SN2 is strong nucleophiles, SN1 is weak. Solvent, and if you keep or retain stereochemistry. I recommend looking at that table. Okay. There's a question about allyl bromide, which is good for both SN1 and SN2, and it asks why. For SN1, you form the carbocation and you get resonance, right? SN2, it's good because, well, there's some complicated reasons why, but allylic carbons are good for SN2. Okay, and then, well, maybe last question, and I'm just gonna include it because it's fun, and even though it's not even as important as the other ones, but just for the hell of it, here we go. Important question. Which of one of these is like SN1 and which is SN2? Which is excellent. I haven't seen this before. I saw it this morning and I was like, I love this. This is excellent. So, well, I'll leave you to think about it. Okay.
Is the middle bottom one SN2?
Well,
Like
well,
the backside
there's
attack.
well, there's 2 rows. Yeah, so there are these 2 rows, right? So
Oh, it's their independent rows.
yeah, the 2 rows. Yeah, so 1 or 2.
The first row is SN1.
Yeah.
One reaction. That's really just like the nucleophile waiting to come into the position. So I have to wait for the leaving group to eject off with the electrophile first.
Yeah. Yeah, and all that's different is what happens in the middle, right? In the end, the orange cat still goes in there. Anyway, I really love this little comic or whatever. This question. I have not seen it before. This is excellent. I wish I knew about this earlier. This is so much fun. Yeah. Okay. All right. We did a lot of review. Hopefully that was beneficial. Yeah. Okay. Oh, oh my God, I always forget about this sign-in thing. So I'm normally, yeah, so I let me stop recording.